Hi, welcome to my channel. Today I'm going to go over curl and divergence, the conservative vector fields, and vector forms of Green's theorem. Let's get into it. The curl and divergence. The curl is a vector and the divergence is a scalar. If f is equal to pi plus qj plus rk, is a vector field on r to the third, and the partial derivatives of p, q, and r all exist. Then the curl of f is the vector field on r to the third, defined by the following. The curl of f is the cross product between the gradient, or del, and the vector field f. And this is how we do it as a cross product. So we have ijk, ddx, ddy, ddz, pq, and r. It's kind of hard to remember the length formula, but you get it from there and you should be fine. So that's how we find the determinant, or the cross product. And that's called the vector field. Theorem. If f is conservative, then the curl of f, written differently because it's conservative, I could replace f with the gradient of f, or del f, will be equal to 0. The converse in general is not true. So what do they mean by this? A implies B does not mean that B implies A. So the curl of f equals to 0 does not imply backwards that f is conservative. Here's another theorem. If f is defined on r to the third, and the curl of f that I called earlier b is available and true, which is equal to 0 now, then you could say f is conservative. So going back is not enough. If besides this condition, f is defined on an open, simply connected region like r to the third, then we say f is conservative. So that's like two theorems in one. What is the curl of f? Since it's a cross product, it's gonna go out of the field. As you could see, we know how to do the cross product, and we know that it's perpendicular to the vectors that you multiply. Particles near the point xyz in the fluid tend to rotate about the axis that points in the direction of the curl of f. That says it clearly with the word rotate. And the length of this curl vector, the magnitude, is a measure of how quickly the particles move around the axis. So in short, the curl measures the rotation of the vector field about the point xyz. If, for example, capital F, the vector field, is defined as follows, let's find practically what's the curl of f. We do the cross product, and simply, it's kind of hard to read all this for you guys, but you know how to do it. For example, to find the k part, you cross this column and you cross this row, and you do the determinant of these four elements: ddx of xyz, ddx of xyz minus the determinant of ddy of xz. Okay? Of course, keep in mind that we go plus, minus, plus, plus, minus, plus. We alternate the plus and minus signs. Doing the math, let's also focus on the last one. Just for example, the derivative of this with respect to x will be yz, as you could see. The derivative of this with respect to y, there is no y in it, so it's 0. Simplify, and that's the curl. Hopefully that was clear. It's hard to remember the lengthy formula, but you just get it from this concept right here. Del cross F. Show that the vector field given right here is not conservative. From the last example, we have the curl of F equals the following. Well, clearly it's not equal to 0. That means it's not conservative. So we say kind of like A implies B is equivalent to negation of B implies negation of A. And that's exactly what we're doing here, all right? Just keep that in mind. This is a negation of B, this is a negation of A. So that's the theorem that was stated at first, the first one. Show that the following vector field is a conservative vector field. Find a function f, small f, such that the gradient of this small f is the vector field f. Now, to do that, we're going to find the curl of f and we know how to do it, similar to last example. But notice, if you take your time, everything cancels. I'm saving you some time, guys, reading this, but you have it. You could just verify the steps. And of course, if there is a mistake or there is any concern, you could leave me comments in the discussion and I'll reply back to you. I will. So if you do the math, you're going to end up with 0. Since the curl of f is 0, and, see, I'm underlining the word and the domain is r to the third. Now, I could say that f is conservative. Without that, I cannot just say that f is conservative and get a full credit. That's the second theorem was stated. So going back, if the curl of f is 0 and you are defined in r to the third, then f is conservative vector field. The domain is all r to the third. Those are polynomials, and polynomials, kind of like, polynomials, they don't have any issues. We don't have fractions, we don't have square roots to take things out of the domain. So the domain is all real numbers in r to the third. Okay, so that should be clear as an example for the theorem number 2. Find a function f such that the gradient of that f is the vector field f, capital F. This is our vector field. Since f is conservative, there exists a function f with the gradient of f equals the vector field f. That means the following. If you compare this f right here to be written as gradient, that's fx, that's fy, fz, that says clearly that this is fx. So I'm taking each piece and writing them here. So we're going to focus on these 3 parts right here. So we take f of x. You don't have to start with fx. You could start with fy. You could start with fz. It doesn't matter. It's just like a game. You go back and forth and finish it. Let's take a look. First, we have fx. We're going to take it back. That means we're going to integrate with respect to x. Integrating with respect to x will give me the following. This is a constant in my point of view with respect to x, so it's going to show an x. So if this is a 5, integrating with respect to x, you're going to get 5x. So you introduce the x, and because of the integration, we need a constant. This constant is not c, like single variable calculus. It could have y's in it, could have z's in it, could have like some numbers in it, but each of these parts will be constants in my point of view. Let me support that. I'll come back to the problem. Here we go. So I'm saying it's a constant. because I'm thinking that x is my variable. For example, if this right here is written as xy to the second z to the third plus y plus z to the fifth plus 7, so it could have y's in it, could have z's, it could have like a number like 7. Finding the derivative to take it back to check with respect to x, this with respect to x will give you y to the second z to the third. This will give you 0, doesn't have an x. This is a 0, doesn't have an x. This is a 0, doesn't have an x. I think that is clear. Let's go back to the problem. Now we have this. Now we're done with this part. Let's move to this part, meaning finding the derivative of this with respect to y and compare it to the second line. d dy will give you 2 is going to go up front because y is my variable. G prime will be called clearly gy because we're doing the derivative with respect to y. Now, with that in mind, compare this underline with the scalar to this right here. That means I don't have that. You could see this right here. There is nothing after 2x y z to the third. That means this should be 0. Well, if g of y is 0, that means it doesn't have a y in it. In the point of view as y being variable, if it's called 0 as gy or g prime with respect to y, that means it just h of z. It has z's in it, maybe, and a constant like 7, but doesn't have a y. So that says f does not have here y's in it, in this part. It just like, it could have z's, it could have constants like 7. Finding the derivative of this with respect to z, now we're moving down, will give me the following. 3 is going to go up front. This will be called h prime of z. I could call it the h with an index z, but we don't have anything left here. We'll compare this to the last part. As you can see, I'm using colors to stay focused. That means h prime is 0. It doesn't have a 0, is a z in it. So h of z could have a 7, but doesn't have a z in it. Finally, that's my answer. You could double check by doing the following. Find the derivative of this with respect to x. You should get that. Find the derivative of this with respect to y. You should get the second one. Find the partial derivative of this with respect to z, and you should get this. And that should do it. It's not hard, but it's something different. And I like to see it as a picture, as a map, to see the flow, how I do it, instead of like writing like a paragraph and so on. So that's my way of displaying things. Hopefully you like it. And as I said, like, it's not really hard. It's just like a game to know how to start, how to compare things, and move on. You could start some other ways. Let's move on. Divergence. What's divergence? It's a scalar field. If f equals pi plus qj plus rk is a vector field on r to the third and dp dx, dq dy, and dr dz exist, then the divergence of f is the function of 3 variables defined by the following. Divergence of f is dp dx plus dq dy plus dr dz. No I, no j, no k, that's scalar field. Differently, it's a dot product. It's a dot product between p, q, and r, and the partial derivatives, d dx, d dy, d dz, or the del, in other words. So what this says, in short, that the divergence is a dot product and the curl is a cross product. Now this section is to show you the difference between them and how you calculate them. On the coming sections, we're going to use them to solve problems. So here we go. Just quick example. To find the divergence of f, all what we need to do is do the dot product between the del and the vector field. d dx of the first component, d dy of the second component, d dz of the third component. The derivative of this with respect to x will be z. Derivative of this with respect to y will be xz. Derivative with respect to z, it doesn't have a z in it, so it's a 0. And that is the final answer. The reason for the name divergence can be understood in the context of fluid flow. If the vector field F is the velocity of a fluid or gas, then the divergence represents the net rate of change with respect to time of the mass of fluid or gas flowing from the point xyz per unit volume. In other words, the divergence measures the tendency of the fluid to diverge from the point xyz. Hopefully that is clear. Instead of going back and forth talking about the divergence, I think that says clearly what's the benefit of calculating the divergence in vector fields as a concept, as an example. Finally, as I mentioned on the front slide, that we're going to talk about the vector forms of Green's theorem. This section is an introduction for the coming sections. You're going to use those ideas and those theorems and apply it. This is the first form, and this is what it says. The line integral of the tangential component of f along C, f dot dr, is equal to the following. The double integral of the vertical component, when you do dot k, you're just taking only the vertical component of the curl of f over the region D enclosed by C. So instead of on the curve, you are inside with the region D, the vertical component of the curl of f. We're going to see some applications and examples on the coming sections, but it's good to have it ahead of time. So this section, as I said, is introduction. Here's the other form. What this says: the line integral of the normal component, when you do f dot n, and n is normal, all what you are doing is you're taking the normal component of f along C is equal to the double integral of the divergence. This is the curl, this is the divergence of f over the region D enclosed by C. Wait for the coming videos, they're coming soon, to see them with examples. Thank you for watching, and I'll see you next time. Thank you for watching. Don't forget to hit the like button, subscribe to see some more, and I'll see you in the next one.